Hello, my warriors. Welcome aboard. I hope you guys can see me and hear me loud and clear. Do let me know in the chat box. Hi, Anthony, Gia, Marla, Harishma, Shri, Jeremiah, Rahul, White Devil. Welcome. Good evening, my lovely and amazing warriors. So, you're watching the Zero to Superhero series, and this series is meant for all the 2022 aspirants who want to crack all the competitive exams this year. This series will be helpful for all the exams, be it SRM, be it VIT EEE, be it JEE, be it NEET, be it KVPY, or your local CET exam. So let's begin. And today's topic is all about semiconductor electronics, and we are going to see the concepts, the formula application, and also in this one short session we are also going to solve lots and lots of questions. Good evening everyone. And like I have promised, there will be also an interesting story, and we are going to learn this chapter in a very different and a very interesting way so that you will never ever forget. Also, my name is Sreyas. I'm the physics master teacher, and if you want to know more about me, yes, you can go ahead to Instagram, and obviously you can learn more about me as well. Check out all my pictures so that you can also interact and you can also send me messages out there. And in today's class, we are going to start with energy bands, then the doping part, the PN junction, both the intrinsic, extrinsic semiconductors. Also, we are going to see the applications of a diode. Then we'll go to transistors. Then we'll also go to the application of transistor, and then finally end the class with logic gates. This is going to be a slightly bigger class, approximately more than 1.5 hours. I'm expecting around 1.5 to 2 hours. So with me, guys. Thank you, Anthony, so much. Hi, Dinesh, Shar. Hi, Pooja. Welcome. Hi, Pratik. Good evening, bacha log. So, if you have not yet joined and hit the subscribe button, do that right now. And thanks to all of you, we are now a family of 100K plus subscribers, and we will continue to grow as and when you grow. You grow, we grow. As simple as that. And when we grow, we get the motivation to conduct more such awesome sessions just for you. And all we need is a small token of love, and that small token of love is your smashing that like button. Go ahead, do that in case you haven't done it yet. And yes, the entire PDF of the session, all the updates, all the important notifications, all the details that you need time to time will be updated on our Telegram channel. If you have not yet joined, make sure you join it right away. Link is there in the description box. So it's story time. Everybody loves story. Vishnu, I'll be doing a 2023 series as well for all JEE NEET aspirants. Don't worry. Many of the students are saying, sir, our exams are going to get over by 29th or 30th of April. So I'm just waiting for everyone to complete their exams in this coming week. And then I will do something for all of you for the 11th to 12th moving students. And then after that 10th to 11th moving students as well. Okay, Shruti, I hope you guys don't fall asleep by these stories. In fact, my idea is to make you awake and make you remember things. All right. Okay, so let's get going. Hi Saja, hi Hari. Looks like you guys are ready. So in this story, we have 3 characters, and at least for the 70% of the session, you are going to see the application of these characters. So that's why I'm introducing them. It's very easy to understand them. Okay, so the first character obviously is Pandu, guys. Okay, so Pandu is going to be one of our character, and before we introduce the next few characters, I want you to also accept or assume certain fact that all the creatures or all the human beings out here obviously want friends, right? You too want friends. When you have a lot of friends, you are very happy. Correct, guys? Now, in this magical world, in our story, even Pandu has friends, and the next character, Champa, also has friends. But Champa has 4 friends. Champa has 4 friends and she is happy. And I will tell you, if you have 4 friends, generally you will be happy because one friend will be in front of you, one friend will be on the left side, one friend will be on the right side, one friend will be behind you. So you are surrounded by friends, front, back, left, right, and you are very, very happy in this universe, in this world. Everybody okay? If you get more friends, then you don't know where to put them. Because already front, back, left, right, you are surrounded with friends. You don't know where to put the fifth or the sixth friend. Everybody understanding this? Yep. So Manisha, this is not 2023 class, this is 2022 class, bacha. 2023 will come very soon. Okay. Next thing. Pandu has one friend less. Okay, let's write it down. Pandu has, let me just put it up over here. So this is our Pandu. Pandu has a deficiency of one friend. He needs a friend. That's why he's singing songs. He's playing the guitar. You're like, okay, please, I need a friend types. Okay. Champa. Okay. Very popular girl. She's a very popular girl. So Champa has no deficiency. So she's happy. She's really happy. You can see the smile on her face. Right, guys? Everybody with me? Good evening, Blessy. All right. Yes, this is also useful for pro students, Marilla, Pallavi. Definitely. The third character. Guess who is the third character? Pandu is over. Champa is over. Somebody more popular. Somebody very dashing. Very beautiful. Her smile can probably get so many guys, on their knees. And, I forgot the A. Thank you, Anthony, for reminding me, or else it became champ. My bad. So, she's so beautiful. She's so pretty, guys. I mean, I had to find a name for her, which is equally, appealing. And her name is Natasha. What's her name, guys? Natasha. Very, very amazing, interesting name, isn't it? So Natasha, that's beautiful Natasha out there. She's very popular, very dashing, and she has excessive friends. She has a lot of friends. One excessive friend. She wants to give away. This guy needs a friend. She wants to give away. She wants to give away a friend. Understood? Everybody clear about these characters? So whenever I talk about these characters, immediately the characteristics should come in your mind. Immediately you should remember, oh, Pandu, he's singing a song, he needs a friend. Champa, quite popular, she has enough friends. She does not need, she does not give. This popular girl, Natasha, she has excessive friends, lot of attitude. I have a lot of friends, types, and oh, yeah, you can just take away one of my friend types. All right. Anyways, so let's start going to our chapter and let's slowly build up on all the concepts that we need to for semiconductors. Great. Now, why semiconductors is so important is because it has revolutionized our entire electronic industry, and it has very unique properties, very different from conductors and insulators. We know conductors conduct electricity when you apply voltage. Insulators block the current or the flow of charges when you apply a voltage difference. Semiconductors is somewhere between conductor and an insulator. When you apply voltage, it allows the current, but very little, not so much. Then you will be like, sir, what is the use of a semiconductor if it does not allow so much also? The problem is, or the point is, the characteristics, the nature of that current changes very magically and very uniquely, very different from a conductor. So you know that in a conductor, when you increase the voltage, Ohm's law, when you increase the voltage, the current increases proportionately. Everybody remembers that? Everybody remembers that, correct? But in semiconductor, guys, it is not so unique. In semiconductor, what happens? It behaves in a very weird manner. And that's what that is what is useful to make so many devices. Your computer chips, alright, your memory chips, so many circuits are based on the fact that the voltage is not proportional to current. No point talking about insulators, because in insulators there is no current only. Alright, now how these semiconductors are made up of, what is in the molecules or in the atoms. To talk about that, a brief small concept of the energy levels and the band gap. See, when you talk about one atom, it has energy levels. 1s energy level, 2s energy level. These are all the orbitals, and each orbital is at certain energy, and each energy level has certain electrons. When 2 or 3 atoms interact with each other, like this is a sodium atom, these are 2, 3 more sodium atoms, when they interact with each other, these energy levels interfere and you get multiple lines. Like 1s of 3 sodium atoms interact with each other and you will get 3 lines of 1s. This is the energy range of 1s electrons for the collective 3 sodium atoms. If there are 5 sodium atoms, the 5 energy lines of 5 sodium atoms will interact and you will get 5 lines over there for 1s, 5 lines for 2s, 5 lines for 2p. So if there are n number of sodium atoms, you will have n lines which are formed for each orbital. Everybody with me? Everybody with me? So as many number of atoms, those many lines for that particular energy level for that orbital. So many energy levels are formed because of the interaction. They interact and they create newer energies. These are molecular energies. And when so many atoms are there, these lines become so close, you virtually can't distinguish between them. You hardly can make out the difference between 2 or more lines. Hence, because you cannot distinguish between these lines, that's why it is called as a band. A band, like you take a paintbrush and you start painting on your canvas, it becomes a band. You take a paintbrush and you paint it like this, it becomes a band. So you cannot distinguish between the lines. You have 1s band, 2s band, 2p band, and so on and so forth. Okay, now what happens is, not all the bands of energy are full. Not all the bands are full. For example, 1s has 2 electrons, it is full. 2s has 2 electrons, it is full. 2p has 6 electrons, it is full. 3s has 1 electron, there is one more electron which can come over here. Hence, when the band also is formed, 1s, 2s, 2p, all these bands are full, but the band of 3s will not be full. It will be vacant. It will be rather half full or half empty. They say, right? Are you an optimist or are you an pessimist? So you look at the glass as half empty or half full. So same way over here, the 3s is basically half filled or half empty. Okay. Now, why is this important? Forget about all this. Now this is important, the bands. You can see bands formed and there is some gap in between. That gap is called as the energy band gap, meaning that's the gap from one orbital to the next orbital, or from one band to the next band, and that is the energy required to make an electron jump from one energy band to the next energy band. Imagine there is some electron here. If you want to make it jump here, you need to supply this much amount of energy, right? You need to supply this much amount of energy, right? Hence, that gap you have to overcome. Think of it like, each electron is now on, a platform. There is a valley in between. What is there? There is a valley in between. There is a green platform. There is a blue platform. An electron can stay on the green platform, it is fine. If it comes here, it falls down, that's it, it's dead. You cannot come in the black region, forbidden region. That is why it is also called as the forbidden energy gap. Have you heard this word? Yes, Rupal, it's coming next week, bacha. Thank you, Sadhvik. Yep. So, you cannot come in the black region, it's forbidden. So, if an electron decides to jump from the green band to the blue band, it has to make a jump, and that is why it is called as the energy band gap. Now, the band which is completely filled, is called as the valence band. The valency is complete. It's complete, it's happy. It's called as the valence band. But all those bands which are not full, which are half empty, half full, or they are empty, they are called as the conduction bands. Like in this case, 1s is full, 2s is full, 2p is full, 3s is not full. So 2p becomes your valence band and 3s becomes your conduction band. Okay, repeat with me, come on guys. 2p becomes your valence band because it is complete. 3s becomes your conduction band. Yes, they will be asked, and White Devil, you will be seeing some questions on this right now. Hold on. Okay, and all these energy diagrams are always drawn at 0 Kelvin. that means no thermal energy has been provided, else the band's energies will be different because the electrons will start jumping because of the thermal collisions energy. Okay, now whenever an electron is in the conduction band, it is available for conduction. When you apply voltage, it will start moving. Keep this in mind. That is why that name conduction band. So in case of sodium, this electron is available for conduction. Keep this in mind. All right. Now, here is what happens when you heat it. When you heat the electrons, basically they are getting agitated. They are given some energy. So the electrons which are in valence band, they start jumping. They start jumping because of that energy. It is like thinking like this. Imagine this is a green platform. There is a black valley gap. You can fall into that. And there is a blue platform. Imagine when you heat, this platform becomes hot. All the electrons which are standing over here, they'll be like, oh my god, my feet are burning. Oh my god, I can't stand over here. But this blue part, the conduction band, that is cold. Think of it that way. Okay, so what these electrons will do, they will jump because they can't bear the heat. They will jump from this platform to this platform. More heat you give, there will be some electrons which can bear more heat. If you give that more heat, they will be like, sorry, I can't bear this higher heat. This is my limit. They will also start jumping and they will start moving to the upper and upper bands. Do you understand this, guys? So when you heat, the electrons can no longer bear the heat and they start jumping to the other higher bands and they are available now for conduction. Conduction. No problem, Bobby. Yes. Thank you, Venkat, so much. Yes. Yep. So in the sodium, yes, 3s is the conduction and 2p was the valence band. Correcto. Now this whole thing decides whether it is a conductor, semiconductor or an insulator. Observe this carefully now. If the two bands merge, there is an overlap. If there is an overlap, then the electrons in the valence band can easily jump into the conduction band. It's like a free path. There is no gap. There is no gap. It's like both the platforms are onto each other. There is overlapping. The electrons will be like, okay, we can just go to the conduction band. They can easily move in and around. So they are very happy to go into the conduction band and so many electrons are just available for conduction. Correcto? Understoodo? Clearo? Moving to the next part. When this gap is very less, you are standing on the platform of valence band. Conduction band is where you should be for you to be available for conduction of electricity. The gap is very less. There is very little chance that you might fall down unless you are really stupid to fall into that gap. So you give it a little push, it will be like, okay, I can jump very easily. Very easily it will jump. So that is a semiconductor. The energy gap is very less, is close to, less than 3.2 electron volt. Now, when you talk about insulators, the band gap is very big. It is like if you have played some games like Prince, Mario or something, there is a big jump you have to do. Very big jump. Even if you take a run up and even if you jump, you might most likely fall into that well. So guys, even if the electrons jump, they will fall. It's not possible to come here. That's why it is an insulator. Understood? Understood? Yes, so it's close to few electron volts. It's very close to 1, 2, 3 electron volts, not more than that. Glad you understood all of this. This is all like a story. If you treat it like a story, you will never forget it. So I hope all these slides are clear. Atoms combining to forming bands, bands having band gaps, and there is a conduction band which is empty, valence band which is full. Conduction band, electrons are available. When you heat the object, the electrons go and jump to the conduction band, and if the band gap is too much, even heating won't be enough to make the electrons jump. That's why it's an insulator. But if the gap is less, a small amount of heat can make the electrons jump, and then those electrons are available for conduction. For conductors, there is no need to heat it also. Already they are available. Perfecto. Let's solve some questions coming up on your screen now. Let's see how many of you are attentive. All right. in a band gap between valence band and conduction band a material is 5 electron volt, then the material is semiconductor, good conductor, superconductor, insulator. Come on, my warriors, spam in the chat box. So Praja, Harishma, come on, Shruti, all right, everybody. All right, saying D for donkey. All right, everybody saying D for donkey. All right, yes guys, it is D for donkey. Perfecto. No, how can it be a conductor, boy? It can't be. Look at this graph. If it is less than some 1, 2, 3 electron volt, then it is semiconductor. This is huge gap. This is obviously insulator. So hence the answer is insulator. Perfecto, excellento. Moving on to the next question coming up on your screen. Resistance of a semiconductor is independent of the voltage, dependent on the voltage, none of the above. Come on, spam in the chat box right away. Is it independent? Is it dependent? Or none of the above? Maybe something else. Okay, figure this out. I told you about this just when I started with the story. I started with some explanation between conductors, semiconductors and insulators. Okay, I can see clear confusion between A, B and even some students are saying C. This is fascinating. That's why you should attend Shreyas sir's classes. Only then you can become superhero, or else you will remain a zero, guys. And the correct answer is dependent on the voltage. Yes. So what happens is, let me get my pen. All right. So for conductors, you will see voltage, okay, is equal to IR, okay, and this resistance is not dependent on the voltage. It is dependent on resistivity, length and area. That's what it is dependent on. It's not dependent on the voltage. In fact, voltage and current are dependent on each other. Now, when you talk about semiconductors, then the voltage decides the resistance, because you will see that only for conductors the graph of voltage and current is a straight line, but for semiconductors the graphs are non-linear. Because they are non-linear, that means at every point the resistance depends on the voltage. Yes, it depends. So you change the voltage, the resistance changes. Very interesting. That's what semiconductor is, guys. Okay, it's not like a normal conductor where it is independent. It is dependent on the voltage. So you will see that non-linearity happens, no problem. Now you know. Don't worry, Jeremiah John. Let's see the next question. An electron in the conduction band is always chargeless, has a tendency to leave the atom, has lower energy than an electron in the valence band, has higher energy than an electron in the valence band. Interesting. Yep. So Venkat, what I said was previously, when the graphs are linear, voltage is directly proportional to current. The ratio of voltage and current is constant. Ratio of voltage and current is constant. So that's why resistance is constant. But when the graph is non-linear, V by I is not constant. Hence, the resistance depends on voltage. As simple as that. Okay, many of you are saying D. Some of you said even B as well. I can see your chats. The correct answer is actually D. Very good, Sonalika, Hari, White Devil, Nilarjan. Yes, very good, Shruti, Daljan, Siswa. Very good, Harishma. Excellente. Anisha, very good, very good. The reason why an electron in conduction band has higher energy than an electron in valence band, you can see it from the energy diagram itself. Look at this. The energy in the conduction band has higher energy than an electron in the valence band. I hope you remember this was the energy level diagram. This is conduction band, this is valence band, this is energy in the increasing order. So when you go to higher energy states, obviously you reach the conduction band. Okay, so that's the answer for that. Moving on to the next question. Let's see what do we have on the screen. Germanium is a semiconductor. Silicon, that's also a semiconductor. At approximately 0 Kelvin, which is very, very low Kelvin, is a conductor, semiconductor, insulator, superconductor. No problem, Venkat. All right, come on, let's see. This is a very tricky question. Many of you can make a mistake. White Devil saying C, Anupama Chini saying D. Okay, Mansa saying B, Rajshekhar saying C, Shruti saying C. All right, Pooja saying B. Oops, Siswa saying B as well. Anisha saying B, Salva saying C. Aishwarya also saying C. All right, Jeremiah saying D. Guys, the answer is insulator. All right, it's an insulator, guys, at 0 Kelvin. I'll tell you why. Going back to our energy diagrams again is very important. A lot of you are asking, sir, is this important? Yeah, these kind of questions do come. You cannot lose marks in this. See, all these diagrams are at 0 Kelvin. Remember, I told you just some time back. Only when you give energy, thermal energy, then it jumps. Now, if you look at semiconductor at 0 Kelvin, it looks like this. There are no electrons here. There are no electrons here, guys. This is vacant. What will happen now if it is vacant? Then at 0 Kelvin, what will you see? What will you see? If there are no electrons which are jumping over to the conduction band, then because there is no thermal energy, it will behave like an insulator. I hope you get that. So when you talk about semiconductor, there are no electrons which have gone. There are no electrons which have gone to the upper band. That's why, because there is no thermal energy, 0 Kelvin. Hence, you will see that it behaves like an insulator. Insulator means there are no electrons out there. Keep this in mind. So, very crucial, this has come in previous years. Okay, this has come in previous years. Yes, so answer is insulator. Keep this in mind, okay? There is no energy. All the diagrams are at 0 Kelvin. Electrons haven't jumped yet. Only when you heat, then they jump, then they behave like a semiconductor at room temperature. At room temperature, they are semiconductors. Now, semiconductors, okay? Samyukta, I will do it probably later on, not now. There's time for that. Perfecto. Yes, it was indeed a nice question. Now comes our 3 characters. You will see why. Now, semiconductors are of multiple types. First is intrinsic, pure, pavam. Have you heard the word pavam? He doesn't know anything. He just knows how to study books. He just knows how to go to school. He listens everything to whatever people are saying or whatever elders are saying, and he comes back home, sleeps, and wakes up early. He's a pavam. Okay, he's a pavam. Semiconductor, intrinsic. Nothing, no external factors. No external factors. Very good. Innocent. Yes. This is not innocent. This is not. Just like my warriors out here. I'm pretty sure nobody's pavam. Anybody pavam? I don't know. You can put it in this category. I don't have any problems. Okay. This is non-pavam people. Country people are here. Okay. So basically, these are extrinsic semiconductors, and they can get adulterated. They can get diluted by 2 things. P or N. P for Pandu, N for P for Pandu, N for what is P? P for Pandu, N for what is N? N for Natasha. Very good. You see, White Devil knows her name. I'm very good, Vandana. You missed some stories. N for Natasha. Very good. See, White Devil already has a crush on Natasha. So those people who joined in late, they don't know how Natasha looks like. What to do? Let's show them. How is Natasha? Where is she? Oh my god. Yeah, there it is. That's Natasha, guys. What does Natasha have? She has a lot of extra friends. And what does Pandu have? His singing songs. He needs friends. What is Champa? Champa, she's happy. One friend in the front, one friend in the left, one friend in the right, one friend in the back. This guy has, one less friend. This girl has one more friend. Keep this in mind. So that is what decides your type of, where is it? Yes, that is what decides your type of semiconductor. So this is where Champa is. This is where Pandu is. This is where Natasha is. Now how does it play? Let's talk about it. Natasha is looking very pretty. See Mansa? No, I mean guys are also having crush. Even girls are having crush on Natasha. Okay. So now what happens is in an intrinsic semiconductor, guys. In an intrinsic semiconductor, what happens is, think of Champa. Just think of Champa. I'll just put it up over here in case you want that reference. Think of Champa over here. Like I said, Champa has formed a covalent bond with another Champa here, another Champa or some other friend here. So happy, very cool, satisfied, no problems in life. But like it happens in everybody's life, you will see sometimes friendship breaks and you make new friends, right? Sometimes friendship breaks and you make new friends. When the friendship breaks, the bond gets broken. Basically, when electron gets free, it starts looking for new friends. Imagine Champa is friends with me. I'm that electron example. That's it. Friendship broke, gone. Katti, okay? I will roam around and find newer friends. Now, Champa will realize, oh my God, Shreyas sir was good. He was good. He was a very good friend. I need one friend back. I miss some friend in my life. So, there will be some other friend which Champa will search for, who will be roaming somewhere else. Some guy like me would have broken friendship somewhere else. That electron will be like, oh, Champa needs a friend. Even I need a friend. Come on, let's form a bond. Yes, I hope this is clear. No problem. Okay, well then all the best. So, guys, what happens is friendships are made and broken and made. So, there are multiple places where friendships are broken, electrons get free. These electrons start looking for newer places to fill in the gaps. And the Champas are also looking for those new friends. And that's what you see in this diagram. Observe this. Observe this. So many places these electrons have broken bonds. See, bonds broken. See that blue bonds are broken somewhere or the other. And the electrons move and the new bonds are made. New bonds are made. Did you see that? Thank you, Aishwarya. Alright. So glad, Sonalika. So, this is what happens inside the entire solid structure. Bonds are made, bonds are broken. Wherever the bonds are broken, so let's say this is silicon, you break the bond, you get a deficiency. That deficiency, what is the deficiency called? It is called as a hole. Deficiency is called as a hole. Hole, you feel that, okay, something will go inside that hole. So that's a deficiency, like when you play golf. And what will come out of it is an electron. It's an electron which will come out of that hole, which has created the deficiency. This electron will go fit in somewhere else, in some other hole, and this hole might be filled with some other electron. And this process keeps on happening. Hello, Hariharan. This process keeps on happening. Everybody clear? Holes keep forming, electrons keep forming, electrons look for newer holes, the old holes look for those new electrons, and then they again form friends, they become friends, and then they again fight, and they again break up, and they again make new friends. This process keeps on happening. Now this process keeps on happening in random directions. So the number of electrons going this way is the number of electrons going that way. The number of holes going this way is the number of holes going that way. So the average will be 0. So there is no net flow of charges. There is no net flow of charges. Everything is equal in all the directions. There is no bias in that. Now let's talk about extrinsic semiconductor, where you dope it, you add something. Yes, we make that Pavam guy, naughty fellow, country fellow. Look at this, what have we done? Oh my God, we got Natasha. So what did Natasha do? Natasha is this one. Do you see this? Germanium, arsenic. Yes, this is Natasha out here. Why we add impurity? You will see that, Rupa. Because when you add impurity, what does Natasha have? Natasha had extra friends. See, in Pavam case, bonds are broken, bonds are made. So the conduction happens completely, it relies on, the conduction will happen and it will rely on making and breaking of friendship. Making and breaking of friendship. But what if you add a villain? And that villain is Natasha over here. Natasha already has one excess friend. That excess friend is getting restless. My God, Natasha does not give me bhav. She does not care about me. I have to look for a friend. That friend becomes angry, starts looking, and because of that electron, the conduction increases. So, doping increases the conduction. You are adding more charge carriers. In this case, adding a arsenic or basically N-type doped material, or when you dope it the N way, basically what is happening is you are creating one extra charge carrier, which is an electron, But please don't be under that impression that n-type is negatively charged. That's the common misconception which many students have. Guys, n-type is not negatively charged. Can somebody tell me why? Can somebody tell me why? Yeah, that friend is electron, correct, white devil. It happens, है ना, white devil? I have also experienced in school. One popular girl will be there, and yeah, you don't want to be this guy, guys. Okay, you don't want to. Never be this. Be this. That's okay. Or be this. Never be this guy, this electron. You will always be like restless. Okay, don't be that. Okay, so atom is neutral, correcto. So if there is an extra electron, there is also an extra proton. Why it is not negative? Because a lot of people have that confusion. Because there is an extra proton. This is a different element, guys. There is a different element. Okay, so what does N represent? N negative, but it's just for your understanding that extra electron is there outside, but it is often misleading. Many people think N is negative, that means actually it is negative. No, that negative stands for that excess negative charge carrier. Negative charge carrier. Yes, I hope this is clear. If you look at the energy level diagram, my warriors, you will see this was your valence band, this was your conduction band. Valence band, conduction band. If you want to jump from this platform to that platform, correct? You want to jump from this platform to that platform to conduct electricity. But the moment you add this extra electron, a new energy layer, a new energy line is created here. Because of which these electrons, so that electron which is here is now here. Now you are creating one extra platform very close to where you have to jump. So earlier you had to jump from here to here. Now you created a new bunch of electrons. We just have to jump this much. So the conduction improves. I hope this is clear. Understood? So you have created a new platform which has electrons which can jump easily. This gap is very less. You can see that this gap has reduced. So hence the conduction increases. Everybody give me a thumbs up and also smash the like button in case you have forgotten to smash the like button down there. Can we move ahead? Okay, so what's next? We have, oh, by the way, I forgot to tell you, Ne is more than NH. What does this Ne and NH stands for? Ne is the number of electrons. NH is the number of holes per unit volume. The electrons are many in number as compared to the number of holes in a given volume. So this is what N-type stands for. Amazing go. Concentration of electrons and holes, correcto. Now, this is Pandu. This indium out here, germanium, this iron is that Pandu. What does Pandu need? He's playing songs, he needs a friend, right? Yeah, look at this vacancy, there is a hole. Pandu is like, I need a friend. He starts crying, he's singing songs. Other electrons are like, wait, I'll come, chill. The electrons jump in here. The moment this electron jumps in here, then this will start crying. You're like, what the hell, man? Why did you leave me and go here? Now what will I do? I will be like, okay, you come over here. And this electron goes here. This will be like, what is this, man? I was happy. Why did you take my electron? They all start fighting for electrons. And in this fight, what happens? Conduction increases. Yes, a doping creates a new platform. Correct, Harishma. You understood the gist. Very good. Exactly. So, in that case, what happens is, usually, if you are a normal PAVM semiconductor, you have to jump this much to reach the conduction band. Now I tell you, wait a minute. You don't jump so much. You only jump till here. That is also fine. I have lowered the conduction band. So that's why that vacancy creates a new vacant, conduction band where the electrons can jump easily. It is like helping them. That's all. And in this case, obviously the number of holes is more than the number of electrons. Yes. Are the new platforms donor and acceptor energy levels? Exactly. So exactly. In the N-type, it's the donor level, and in the case of P-type, it is the acceptor because electrons jump onto it. I hope this is now clear. Perfecto. So let's start solving problems. Oh my God, you are already going to start solving problems. When a solid with a band gap has donor level just below the empty energy band, then the solid is insulator, conductor, P-type, N-type. Come on. Everybody should answer this now. I have taught you guys so well, you can never make a mistake. Come on, my warriors. Figure this out. What should be the correct answer to this? All right. Somebody already starting to type the answers. When the donor level is just below the, empty energy band. Empty energy band is conduction. Yes. So what will it be? It will be N type of semiconductor. I just showed you right over here. Remember, Natasha, extra electron. Extra electron creates a new platform full of electrons which can find it very easy to jump from here to here. So it's just below the conduction band. Hence, the answer is N type. Perfecto. Moving on to the next question. When the conductor of a semiconductor is only due to breaking of covalent bonds, the semiconductor is called intrinsic, extrinsic, P type or N type. Okay. I remember Vicky Donor. Now this is a new movie. Natasha Donor. Okay. All right. Let's see this. When the conductivity of semiconductor is only due to breaking of covalent bonds, now the semiconductor is called as, yes, the PAVM, covalent bonds only. Covalent bonds get broken. There are no electrons or holes which are creating that breaking of the bonds. Yes, it is the PAVM semiconductor, intrinsic semiconductor. Perfecto, Siswa, Menu, Hari, Aishwarya, Harishma, Hari, Rajshekar, Vijay, very good Shruti, Sonalika, excelente White Devil, very good Chandaleka, excelente. Moving to the next question. In N-type semiconductor are obtained when germanium is doped with. If you have been paying attention, you know what should germanium be doped with so that it becomes N-type. Natasha, who is Natasha here? Think, who is Natasha here? Yes, think about it. Is it arsenic? Is it phosphorus? Is it antimony? Or doesn't matter. Any of these? I just showed it to you. Look over here. Let's go back to Natasha's slide. Yeah, there you go. This AS, what is this AS? Arsenic. Yes, perfecto. So for germanium, it is arsenic. Okay. Some of you might have also seen phosphorus. Like, sir, in one book I had seen phosphorus also. Phosphorus is used, but not for germanium. It is used for, how many of you can tell me this? It's used for silicon. Yeah, it is used for silicon. Because it should be in the same row of the periodic table. You have to dope the element with the same level in the periodic table. The row should be same. Yes, keep this in mind. Okay, that's how you have to remember it. It should be the same level. Okay, now moving on to the next one. This is formula based questions. Okay, now trivalent, that's for silicon, trivalent impurity will be aluminium, Al. Al is used for silicon. Keep this in mind because it's at the same level, same kind of energy levels are there. Okay, now the concentration of electrons and the holes is given by Ne and NH. Electron concentration and hole concentration. Usually in an intrinsic semiconductor, what happens? For an intrinsic semiconductor, so if I put it over here, for intrinsic, PAVM, remember that Ne will be equal to NH, and usually this concentrations, because they are equal, I represent or call it as Ni. This I stands for intrinsic. Okay, this is for intrinsic, Ni. What is this? The concentration. So when I say concentration, it means the number per unit volume. Okay. Now, if you dope it with P type or N type, so that non-PAVM types, whether it is N or P type, then for extrinsic semiconductor, Ne into NH, the product remains constant and it will be Ni into Ni, which is Ni square. Basically, Ne into NH is constant for any given semiconductor. So for intrinsic, it was the same. So Ne into NH will become Ni into Ni, which is Ni square. So this is the formula which you need to definitely know. And this is for intrinsic. Okay, I hope this is clear. So glad, White Devil. Now, the next formula which you should know is for mobility and conductivity. How many of you remember that formula, guys? How many of you remember that formula for mobility and conductivity? So what is mobility? How mobile the charge carriers are. Mobility. Okay, I'll just put mobility. Yes, mobility. The symbol is mu. It is the drift velocity per unit electric field. This is mobility. How much is your speed per unit electric field which is applied? Why is electric field there? Because when you apply voltage, when you apply a battery's terminal, okay, voltage, there is electric field which goes from high potential to low potential. Because of the field, there is force. Because of the force, the electrons move. So how much is the speed per unit field? That is called as the mobility. Next important formula, conductivity. Conductivity. The conductivity of any semiconductor is because of electrons and the holes, and in general the formula for conductivity happens to be N, the charge carrier density, into mu, which is mobility, into the charge carrier itself. Okay, usually this is the formula for conductivity. But because it's a semiconductor and the conductivity is because of electrons and holes, this will come for electrons, this will also come for holes, and you will get a total formula which looks something like this. It will be number of electron charge carrier density into mobility of electrons into the charge of electrons plus the number of hole density into mobility of holes into the charge of the hole. Hole is having the same magnitude of charge because one electron less creates plus E charge. So charge wise, this is also the same. So this is your conductivity formula. This is your conductivity formula. Sigma is NUE. That's it. Yes, VD means drift velocity in case you did not know about it. Yes, this is your drift velocity, and this E is your electric field. Okay, mu is your mobility, E is your charge, 1.6 into 10 to the power minus 19. Okay. So are you ready for solving some questions? Yes, definitely, Berlin, but you need to solve some mock tests, you need to solve some assignments, not just attend classes. Can you start driving a car or learn a bicycle by just watching videos? If I see the video of how to fly an aeroplane on YouTube, it is there. Can I learn? No, right? I need to practice. So you also need to practice, bacha. Keep this in mind. Okay, let's solve this question coming up on your screen. The conductivity of an intrinsic germanium at 300 Kelvin is how much? If the intrinsic charge concentration is 10 to the power 13 per centimeter, the mobilities are 3800 and 1800 centimeter square per volts second respectively. Okay, this is very interesting. Warm light turned off, I think. I'm not sure. Maybe there was a power cut, maybe the power is back. Yep. Yes, definitely, Shruti, I will definitely make it. I just want to complete the Zero to Hero superhero series for the term 2 topics, which is the last one is ray optics. After that, I will definitely have all the strategy and the board sessions which you are demanding for. Okay, so what's the formula? Sigma is equal to number of electron charge carriers. It's an intrinsic. So, okay, let's just put it Ne mu E into E plus NH mu H into E. Now Ne and NH, they both will be equal to Ni because it is Pavum semiconductor. So Ni comes outside, E also comes outside. What is left is mu E and mu H only. So just start substituting. Ni is 10 to the power 13. You don't have to convert it into SI because the units will get cancelled. The units will just get cancelled, so don't bother about it. Electron charge is nothing but 1.6 into 10 to the power minus 19 and into this plus this, which is this and this together, which is 3800 plus 1800. That's it. Solve this and see what you guys get. Come on. Yes. Are you getting option B? Yes, it is B. In fact, it is B, guys. Perfecto. Excelente. Everybody understood this? Yep. There we go. Yep. See, guys, Abhi's Purakrit is a Pandu. Do you see one Pandu in the chat box? See one Pandu in the chat box. How many of you noticed Pandu? And somebody is Natasha out here. Who is that Natasha? Who is Pandu? We have live examples, guys. Okay. So moving on to the next question. Yeah, so there we go. On applying an electric field of intensity 10 volt per centimeter, a semiconductor at a certain temperature, the average drift of the free electron is 70 meters per second, then the electron mobility is, what is the electron mobility? Come on my warriors, figure this out. What is the formula for electron mobility? The electron mobility formula is the drift speed upon the electric field. Come on, figure this out. What is the answer? Be careful, this is in meters per second, this is in volt per centimeter. So that means you need to convert the meter into centimeter. So 70 meters per second will be 70 into 100 centimeters per second. Now you start solving it. So it will be 70 into 100 divided by electric field, which is nothing but just 10. This 0 cancels. So it will just become 700. This will be in centimeter units, which is option B. Yes, option B is correct. Just check this out. Yes, it is. Understood? Oh, clear? Oh? No, it is not D, bacha. It is not D. Be careful. The units are very important. The mobility units, just check this out. It is usually in centimeter square. See, it's centimeter square, okay, per volt second. So be careful. Option D also has 700, but the units are wrong. So that's why it is confusing. Yes, so be careful. Electric field of intensity, guys, you would have heard the terms like magnetic field intensity, magnetic induction. They all mean the same thing. B. Electric field strength, electric intensity, electric field of intensity, they all mean E only. Don't get confused. Nilarjan, just replace that T in the link with telegram.me. It will work. It will work. Okay, what do we have next? Let's see. The concentration of minority charge carriers in extrinsic semiconductor under equilibrium is, come on, think about it. Those of you who did not understand the question, concentration of minority means, see, if it is N type, N, that is electrons will be more, holes are less. Who is minority, you think? So in extrinsic means P or N type under equilibrium is. There is a simple law. Let's see. Okay, no problem, Bobby. Okay. So, yep, is it C? No, it is D. It is inversely proportional. See, if it is a p-type semiconductor, then electrons are minority. And holes are majority. And what did we just see some time back? Ne into NH is Ni square. So the product is constant. What does it mean? Ne is inversely proportional to NH. Inverse. So it is inversely proportional to the doping. So in this case, the holes are majority. So this is your doping concentration. You're doping holes to make it p-type. You're doping holes to make it p-type. And electrons are minority. It's a p-type semiconductor. Hence, the minority is inversely proportional to the doping characteristics. I hope this is clear. Moving on to the next question coming up on your screen. Oh, we have the next theory actually, and then we'll go to the next questions. Perfect. With me, everyone? All right. So now we are coming to PN junction. PN junction. Imagine Pandus and Natashas together. Imagine Pandus and Natashas together. Where is this Pandu and Natasha? Where did they go? Let's see. Yeah, imagine Pandu needs a friend. Champa can give a friend. Both come in front of each other, and not just one Pandu, one Natasha. Many Pandus and many Natashas. Many Pandus and many Natashas. Siswa, you can take the example of N-type also. It's valid for both. Okay. No, Champa is happy. So that's why we are not taking example of Champa. Okay. So, where did it go? Yes. So, come on. Yes, there we go. Alright. Now, when you have Natashas which have excess friends, and Pandus, P region, which need friends, which have holes, the extra friends who Natasha has, they will be so happy. They will be like, okay, we have people who need us. They will start running towards the Pandus. Everybody agrees? Thank you, Rashmi, so much. All the excess friends, they start running towards the Pandus. Now the moment they run, lot of problems happen. And let's see what happens. First thing, the moment they meet, the electrons from N jump to the P, the friends from Natasha go towards Pandu. That process is called as diffusion. They diffuse. All the friends start running towards the Pandus because they need friends. That is called as diffusion. The electrons which are moving, or the holes which are moving in this process, they set up a current. So there is a current which is going from one side to the other side because of the flow of charges. That current is called as diffusion current. I'll repeat. What is diffusion current? The moment two different extrinsic semiconductors, p-type and n-type, are brought close to each other, the n-type has excess charge carriers, p-type has deficiency or holes. The electrons immediately jump and the holes get transferred. So the flow of charges causes diffusion current. What's the direction of the diffusion current? Is it from n-type to p-type or p-type to n-type? Come on, answer this in the chat box. What is the direction of the diffusion current? Is it from n to p or is it from p to n? Let's see how many of you can get this. Very tricky and simple question. Very tricky and simple question. Come on, figure this out. From n to p? No, it is not n to p. Be careful. It is from p to n. Be careful. N is negative. When electrons go like this, current is the flow of positive charges. So actual current is going from p to n. Actual current is going from p to n. Made a mistake, na? Happened. There you go. See? Yeah, opposite to the direction of electrons. So diffusion current is like this. Keep this in mind. Okay. Now what happens? The next problem happens, and that is the drift. So look at this. This graph also tells you, this is n region, this is p region. So you will see that the electrons, they will start moving towards, the electrons will start moving towards the p region. You can see that they are easily moving towards the p region. And because of this, because they are filling up the holes, you will see that there will be a potential difference which is created. Because now actually N will become positively charged and P will become negatively charged. Look at this, positive charges. N becomes plus, P becomes minus. Potential difference created. Barrier. There is a barrier, potential barrier which is created. Why this barrier has come? Think of it this way. Okay. By the way, these kind of questions can be also asked in a PN junction. Then N becomes negative charge, positive charge, or neutral. Lot of people will think N negative. Some people will be intelligent. No, sir had told N is neutral. But you guys forgot, N is neutral if it is independent, if it is separate. But when it is brought in the proximity of p type, then the electrons will jump. And electrons jump away from it, obviously it will become positively charged. Okay. Now, like you can see in this graph, this is energy graph. This is n type, this is p type. Majority carriers are n electrons. Here, majority are holes. So you will see the moment they are close by. Observe this animation. These electrons go to the p region. So there will be positive charges developed here, negative charges developed here, positive, negative, potential difference. The moment charges are there, charge separation is there, there is electric field. So there is a potential difference which is created. This potential difference is created because of the electric field. Remember, electric field is nothing but, how many of you have forgotten this? Electric field is nothing but del V by del R magnitude wise. Potential difference per unit distance. So because there is electric field from positive to negative charges, there is a potential difference which is created. Now because of this potential difference, that is why you call it as a potential barrier. this potential difference will stop or will prevent more electrons from jumping to this side. What is a barrier? Barrier is you stop something. When you put a barrier, you can't go to the other side. This is a potential barrier. Del R is the distance between these 2 points. Distance between this end to this end. So there is a potential difference. Hello Indu. Okay, white devil, I hope you understood this. Okay. So now what happens, guys? Okay, what happens is, because there is a potential barrier, the electrons will find it difficult to jump to a higher potential. The electrons can't jump to a higher potential because of that barrier itself created. Yep. Initially the barrier was 0, correct. There was no barrier because there was no field. Was there any field? No. Was there any charge? No. It was neutral. Because the charges came, that is why the field came, that is why the barrier came. It is like saying all the Natashas lost their friends. All the Natashas lost their friends. Now those popular girls are thinking, I was having that attitude. I was having my charm because I had more friends around me. I miss my extra friend. Although I did not have very good friendship with that guy or that girl, but that friend made my popularity because I had excess friends. I miss him. So the remaining Natashas will be like, please don't go, stop. So there is a barrier created. They realize, self-realization is happening. In this side, Pandus were always like, I need more friends, I need more friends, I'm playing the guitar for you, I need more friends. When these friends came, then it was a headache for them. It was a headache. They're like, okay, stop. I don't actually need these friends. So there is a barrier which has been created. There is also a reverse process which occurs. Okay, there is also a reverse process which occurs. The electrons from this side also start going to the other side. Because remember, some Natasha started regretting. There was a regret. Remember, they started repenting. And this electric field is which pushes or which pulls those electrons from here to here. Remember, if field is here, force on electrons is this side. If field is here, force is on this side. So the Natashas who started regretting, they will be like, please come back. Please come back. It's okay. You stay around me. And these electrons which went there, these Pandus are like, okay man, I don't want, it's okay. I'm fine with having 3 friends also. You go back. Then this friend is like, okay, this guy does not need me. Pandu does not need me. I'll go back. I'll go back. Natasha, okay, fine. I'm coming back. Yeah. Is that clear? Yep. Yeah, definitely Aarti. But please attend from the start because you need to know who Pandu is, who Champa is, who Natasha is. Yeah. So that is when these electrons which are going back, they create a new current. That current is called as drift current. They start drifting back. What did they do? They started drifting back. So these electrons have regretted their decision. Natasha was good. It's okay. She has attitude. No, it's okay. Fine. But at least she did not insult me like Pandu did. Pandu is like, go away. Pandu does not even have friends. He's like, go away. Okay, fine. No problem. You won't go back. So both the currents are established. Diffusion current, drift current. Diffusion current, drift current. Both currents are opposite. If both currents are opposite, what is the total current? If both currents are opposite, what is the total current, my warriors? Very good, Meenal. Excellent answer. Hello, Surya. Long time. Both currents are equal and opposite. Hi, Suwani. Then the net current is 0. It is 0. Pandu was insulting Mansa because Pandu had less friends, holes. And Pandu, when these electrons came here, Pandu was like, you go back. It's okay. I was okay with 3 friends. You are creating new troubles in my life. So insult from Pandu. That's why these electrons went back. Very good. The difference of both currents will be 0. Why should there be current, guys? For no reason. So there is an equilibrium which is created. Dynamic equilibrium. You would have seen that in chemistry. Diffusion current, drift current. Dynamic equilibrium. Perfecto. How can you say electrons drift? Drift means basically the electrons. See, electrons are there everywhere. So because of the field, what will happen? There will be a force. That force will be applied in this direction. That's why I can say with proof that electrons move from this side to this side because of the field created. Is that clear? Surya, just practice, have confidence, study well, don't study things which you don't know. Study things which you know. Okay? Alright. So, focus only on the important things. Focus on scoring marks, not focus on completing the theory. If you focus on completing theory, you will lose marks. Alright. Now, forward bias and reverse bias. These are the two biases. Remember, Natasha gave away friends. Pandus needed friends. There was an equilibrium created. Now you create some external agent. Basically a battery. You apply a potential difference. Imagine the positive terminal is connected to P, negative terminal is connected to electrons. Just imagine, guys, what will happen. Negative will create more electrons. It will pull in or it will push in more electrons in the N type. Positive will pull those electrons from here. So you will see the diffusion which was occurring from the N to P type, that is helped, that is being biased, that has been, it's a partial behavior. You are doing partiality. How are you doing partiality? Partiality means, biasing. You are biased in opinion. You have a bias towards this guy because he or she is your favorite. So you are giving favoritism to the diffusion current by creating a positive potential over here. So that pulls those electrons which were jumping from here to here, you are pulling them. And by pushing them, by applying a negative voltage, so which pushes those electrons inside. Is that clear? So I hope Hari Krishnan bias understood. Did you understand bias? The teacher is biased towards the toppers, meaning the teacher is partial towards the toppers. Whatever the topper say, teacher is like, okay. The topper say, ma'am, extend the homework deadline. Okay, teacher is like, okay, fine. Backbencher says, please extend the deadline. One slipper will come or one duster will come on his face. So that is bias behavior. That is partial behavior. Okay, fair enough. So now, this is P type, this is forward bias. So you will see electrons start flowing in the circuit. The Natashas will give away their friends to Pandus. Pandus will give the friends over here. There is some guy who is in like desperate need of friends. Please give me the friends. Pandus is like, take this friend. And there is some very, very interesting source of friends. A lot of friends are coming in over here. These Natashas are getting fed up. My God, already I had so many friends. Now more friends are coming. Okay, Pandu, you need some friends? Take. Oh my God, one more friend came. Okay, Pandu, you need a friend? Here, take. Pandu is like, okay, I got the friend, but this guy, he is in more need. Okay, give that friend over here. So that's how things are over here. Yes, and he started donating. Correct. All right. Now, reverse bias. In reverse bias, you are exactly opposite. The P is connected to negative, N is connected to positive. We'll see what happens. N is Natasha. Natasha has extra friends. Natasha wants to give the friends to Pandu. Pandu needs the friends. But you tell Natasha that there is one more guy or one more bunch of people who are desperately in need of friends. Desperately. They're like pleading, please, you have those extra friends, give to me over here. Natasha is like confused now. Should I give it to Pandu? Should I give it over here? Should I give it to Pandu? Should I give it over here? This person, positive, is asking my negative charges, pulling. This Pandu also needs. That's it. Confused. Here also, Pandus are like, Natasha, please give me your extra friends. From here, this negative terminal from here, please give me that extra friends. Pandu is also like, what the hell is happening? I only don't have. Okay, both are asking. Yeah. So basically, there will be no current which will be flowing over here. What will happen? There will be no current which will be flowing. In fact, there is a very small, teeny, mini current which flows forcefully because of this positive charge, positive potential, giving those electrons deliberately by force. Like, take. Natasha like, why are you, wait. Well, I already have. I already have. So it's creating problems over there. Okay. So there will be a very small current which will be flowing, and that is so small. That's why you say in reverse bias, there is very little current. There is very little current. What is the use of negative biasing? Now you will understand it. Shruti, you know that our heart has pipes which come out of the chamber. Our heart pumps blood. It sucks blood and pumps blood. Obviously, the blood which goes out of your heart should go in the correct vessel, and the blood should also come inside the heart from that correct vessel. What if you pump the blood into that vessel from which it is supposed to enter? That will create a problem. That should not happen. Okay? It should not happen. Okay. So what is happening over here is that when you bias it forward, electricity flows. When you connect it in reverse, electricity does not flow. It's acting like a valve. What is it acting? It's acting like a valve. There are valves in your heart which make the blood flow in one direction only. The blood does not flow in multi-direction. It's not like two-way traffic. It's one way. The moment you go in that wrong lane, there is a policeman. He will whistle and is like, wait, go back, U-turn, one way, sorry, no. Even if you pay money, nothing will happen, one way. So that is called as a diode. Diode is one way. Diode is one way. Understood, got it, very good, excellent, perfecto. So that's why diodes are like walls but for electricity. Just like your human body or any animal body has walls inside their heart, there are walls for electricity also. Only it will allow electricity in one direction. Other direction, gone. No. Sorry, go back. Sorry. No. How many years I studied in NIT and IIT? Hari Krishnan is asking. Hari Krishnan has his doubts that sir did not complete his engineering in 4 years. He's thinking I completed my engineering, God knows, 1 year or maybe 10 years. Who knows? Thank you, Amazon Park. Love you too, bacha. Thank you, Neelarjan. Very good, Mansa. Excellent. So, the diode symbol is this. This is the triangle. The triangle points in the direction where it allows the current. If it points this way, it will allow here. This way, not allow. Okay. This is how a diode looks like. This is how it looks like. Actual figure. It's very teeny meaning. Okay. Now, this is the very important graph. Very important graph. Very important graph. Thank you, Paray, for all the love from Kashmir, and so glad Amazon Park. All right. Bad Buddy Gaming. Bad Buddy. Oh, it's not Bad Buddy. Oh, sorry. It is Bad Buddy. Bad Buddy. Oh my God. What am I saying? All right. So what is this? This is current versus voltage graph. Current versus voltage graph. Did I not tell you at the starting of the class? Voltage is not proportional to current for semiconductors. For semiconductors, voltage is not proportional to current, and you can see that over here. When you apply positive voltage, meaning forward bias, current flows. Zoop, current flows very nicely. But when you reverse bias, this is very small, very teeny meeny, current does not flow. So current flows, current doesn't flow. That's how this IV characteristic, current voltage characteristic of a diode. For a conductor, it is one straight line. This is how it is for a conductor. It's one straight line. It is linear. But for a semiconductor, it is non-linear. Resistance is not constant. Thank you, Bachalok, for all the love from TN. The place where I was born. Yes, your Shreyas sir was born in TN. Not many people know that. Okay, so oh my God, we have some questions coming up on your screen, and here it is. Which of the following semiconductor diodes is in reverse bias? Kaveri Delta. Hari Krishnan, are you with crocodiles or hippopotamus? For insulator, there is no graph answer. There is no current only. No current. What is the point of drawing the graph? Thank you, Sonalika, for all the love from Odisha too. Sir, graph 1 minute. White Devil, you can go back. Even in a live class, you can slide the slider little bit and you can go back. Yeah. So very, very important. Okay. Let's see how many of you can answer this. Neveli. Oh, where is this place, Shruti? I have Not heard of this place. Everybody saying A, is it? Option A for sure. Done, done, done. A for apple, B for ball, C for cat, D for donkey. Apple, ball, cat, donkey. Okay, it's apple. Very good, excellent A. And why is it so? See guys, ground means 0 volt. This is the direction of the flow. This is at lower potential. This 0 is obviously higher than -5. How can current flow like this? This is obviously reverse bias. If you see over here, 10 to 5, obviously it can flow from high to low. Correct. This is a forward bias. 10 to 5, obviously this is forward bias. This is high, this is low. This is -5, -15. This is again high, this is low. So obviously it can flow. Correct. Very good. The lignicity. Oh, you get lignite over there. Interesting. Okay. Madurai. Hari from Madurai. Madurai idlis. Oh, I love the food in Madurai, man. It's amazing. Yeah. So, from Coimbatore too. Oh my God, look at that. I get to know where you guys are from too. Okay, so the conduction in the PN junction in forward and reverse bias is due to drift, ionization, drift, diffusion, diffusion, drift, diffusion, radiation. My God. Yes, I know white devil. Look at that. So everybody, we get to know everybody's place now. Yeah, so the conduction in PN junction in forward and reverse bias is due to in forward, remember forward bias, diffusion. In reverse bias, drift. Yep. Recollect this. I'll show you the diagram also. This was forward bias. In forward bias, it's because of the diffusion. The electrons go from here to here, which they were eventually anyways doing. The electrons were jumping from here to here. So that is the diffusion current. So in the reverse bias, it's the reverse current. So the current flows in the opposite direction. That's your drift current. So guys, remember, it's always diffusion for forward, drift for reverse bias. Adi boy, this is an adult class. Okay, only for adults. Underage students can't attend this. Lot of adult material is there, adult stuff. Please don't attend this class. Okay, only students who are above 16 can attend this class. Okay, see, all right. So let's see the next thing. Tabu, thank you, bacha. Love from Chennai too. Okay, where am I presently, Paray? I am in Bangalore. Okay. So how to avoid silly mistakes in physics? Martilla Pallavi, simple. Concentration, meditation, focus, and not being nervous. As simple as that. Okay, so what do we have over here? Applications of PN junction diode. LED is there so many places, right? In your torches, yeah, in your torches, in the computer screens, in your so many electronic devices, LEDs glow. In your indicators or headlights. So that's a LED, that's also a diode. Now, basically, the symbol of a diode, you should know it. The symbol of a diode, same normal thing, but just show 2 arrow marks coming out of it. That becomes your LED, light emitting diode. Why is it called LED? Light emitting diode, it emits light. Why does it emit light? Because when the electrons flow and jump from one place to other, they jump energy levels. When they jump energy levels, they emit photons. And if these photons are in a particular range, they emit that color wavelength. So you can have green LEDs, red LEDs, blue LEDs, depending on which photons are emitted during the electron transition. Thank you so much, Paray. Now, the next thing is your photodiode. Guys, I understood the importance of photodiode when I first went to a 5-star hotel when I was very young. I had never seen 5-star hotels. There, our usual thing, we went to the wash basin to wash our hands. I didn't know where the knob was. I tried to press everything. Some random liquids also came out, soapy liquids. Then, some toilet paper came out. But the water is not coming. Then I just kept my hand. Suddenly, water came out. I'm like, my God, this is so magical. And then I just kept on doing this. Like this. And then the water comes. And then it do this, the water does not come. Then the waiter over there gave me an angry look. So I had to run away. Then later on I understood in 11th and 12th standard that was a photodiode there. This is what it is. Yeah. From jumping how they emit photons, I'll tell you why. Devil, 1 second. So what does a photodiode do? It is, the conductivity is based on how much light falls on it. How much light falls on it. So reverse arrow marks. Reverse arrow marks. So when light falls, it has a separate conductivity. And when you block the light, when you put your hand, then the conductivity changes. It triggers the circuit. It opens up, the valve, and the water starts flowing. There is a pump. There is an electrical motor which pumps in. So that's how it works. Yeah. So LCD is liquid crystal display, LED is light emitting diode, two different things. Okay. From jumping how they emit photons, white devil, simple. In an atomic structure you would have studied, electrons jump from ground state to higher energy state by absorbing photons. When they jump back from high to low energy states, Bohr's theory, what do? They emit photons. So when the energies change for electrons, you will see the difference of the energy corresponds to the energy of the photon. Yeah, very good. Even you realize it, Shruti. Very good. Okay, understood? Clear? Yes. Aisha, looks like you did not attend my class yesterday. So I started wearing glasses from yesterday. And I don't have a power, but it looks cool. Number one. Number two, it looks cool as well. And number three, it protects my eyes. So that's the reason. The three reasons why I'm wearing the glasses. Is it clear? So next time anybody asks why Shreyas are wearing glasses, you should give all these three reasons. All the three reasons. The first two are very important. Third one is not so important. Alright, moving on to the next one. Oh my god, what is this girl doing out here? Zener diode. Thank you, Bad Buddy Day Gaming. Anti-glare glasses. Yes, Sriharshan. Okay, so have you heard of the word Zen? What does Zen mean? Zen means relax, at peace. You don't bother what is happening. Like this girl out here. She's at peace. She's meditating nicely on the beach. Right? So, Zener diode is also in the Zen mode. They say, you're in Zen mode. So, Zen is a car also, I know, but even I have a Zen car, guys, at home. Yeah, it's still working. Yeah. So, a Zener diode basically is at peace, meaning it doesn't bother of some voltage fluctuation, it maintains the voltage. So, it's a voltage regulator. Natasha, after losing friends, and it is meditating. Very true, Mansa. Yeah, very true. That was Natasha meditating after losing friends. That's the best line. We should highlight, we should pin this chat up. I hope the admin is listening. Okay, so a Zener diode is used to regulate the voltage because it operates in reverse bias. If you remember, the voltage characteristics, current and voltage characteristics, this was your forward bias, this was your reverse bias side, and the graph looked something like this, and it goes like this, and then it falls flat. So here you will see that the voltage is constant. In the reverse bias, the voltage is constant. So if you use Zener diode in reverse bias, in this region, this is called as the breakdown. In reverse also current flows, but after a certain limit, that is called as a breakdown. It's like finally gives up. Finally gives up. Thank you, Thalapati Giri, so much. So that is your breakdown voltage. So in reverse bias, if you connect this Zener diode, what happens is, so let's say this is connected to, I don't know, maybe plus 10 volts, and this is your ground, let's say, and maybe there is a resistor over here. So, okay, wait, let me just draw it in a little bit better way. All right. So you have a resistor, goes like this, and this is connected to 10 volts. Let's say the breakdown voltage, example, I'm just giving an example. Example, the breakdown voltage for the Zener diode is 3 volts. Example. This Zener diode, no matter what you do, it's in Zen mode, it won't care. It won't care. It will maintain 3 volts. It will make sure across these 2 points, you will get 3 volts. You'll be like, sir, but you applied 10 volts, sir. What happened to the remaining 7 volts? The remaining 7 volts will be dropped over here. The remaining 7 volts will be dropped over here. Got it? So, if you make this 10 something else, This will still remain 3. The difference will be dropped elsewhere. That's what a Zener diode does. Clear? Understood? It works in reverse bias. Zen, stay constant. Keep this in mind. Alright. Next few applications. Rectification. Rectification. What is rectification? Rectification is the process of converting AC to DC. Rectification is process of converting AC to DC. What is the reverse process called? From DC to AC. Let's see how many of you have the general knowledge. Very simple general knowledge based question. Probably can come in CUET exam or even be asked in, I don't know, KVPY exam or maybe some CET exam. Who knows? What is the reverse process of converting DC to AC called? AC to DC, rectification, anti-rectification. Very smart, Siswa. Siswa, what an answer, bacha. Excellent, bacha. Anti-rectification. Reverse rectification. Who is it? Naz. Wow, very good. Mansa, amplifier. No. Okay, I'm getting funny answers and I'm loving it. Okay, so guys, what is the correct answer? The correct answer is not anti-rectification or reverse rectification. It is called as inverter. Inverter. Normalizing. No, you guys have inverter in your house. KVPY is an exam, Hari Krishna, through which you get admission in good colleges like ISC, ISR, IST. Also get scholarships for doing pure science courses. So, you always must have seen that there is an inverter because you store electricity in the batteries. Batteries give DC, but your house has AC. So, from DC to AC, you have an inverter. Yes, virus inverter from the movie 3 Idiots. Remember now? Perfect, White Devil. Very good. Understood. Now, AC has positive cycle, negative cycle. Positive means current flows one way. Negative means the current flows the other way. So, that's the meaning of a positive cycle and a negative cycle of a AC current. So, you would have seen AC current is shown like a sine wave. AC current is shown like a sine wave. When I say positive, it means it flows one way. When I show negative, it means it flows the other way. Now, if you have a diode in the circuit, then it allows the flow of the current in one way, but when the current is in the other cycle, the negative half of the cycle, then it does not allow current. So, if this is your AC signal, which is basically your input, this is basically your input, then your output, which is over here, your output over here is this one only, because during the negative cycle, the current can't go through the diode, it blocks. It's a one-way traffic, remember? So it blocks. There is this current, block. This current, block. It only allows current in one direction. So you can see the current which was changing the direction, first this way, then this way, is now going only this way or not moving. Only going this way or not going. So it has converted from AC, the output is now a DC current. Is that clear? Is that clear? Perfecto. The other rectification, this was called as a half wave. Why half wave? Out of this complete wave, only half of the wave came here. Half just got eaten up. Hungry rectifier this is. So the other rectifier is called as a full wave because the entire AC is going to get converted. It's like taking modulus. If this is sin x, this is like taking modulus. Do you see that? Modulus of sin x. Think of it like this. If this is sin x, this is like mod of sin x. Does it make sense? It's like whatever was there below, you put it up. So now you have current which is only in one direction. It only flows like this, like this, like this. So that's a DC current. How does it work? You have two diodes. In the positive cycle, when the current is going like this, it flows through diode D1. It flows through diode D1. But in the other half of the cycle, when the current comes from here, then it flows from diode D2. And you will see every time it flows from B to A, whether it goes from here to here or whether it goes from here to here. So every time, since it is going in the same direction, it's going in the same direction. That's why you see the graph like this, the current through the resistor AB. Hence, it becomes a unidirectional current, which is efficient. Obviously, full wave rectifier is double efficient than your, normal rectifier or half wave rectifier. I hope that makes sense. Is that clear? Okay. So let's start doing some questions coming up on your screen. Oh, no problem. Dhaya, Niti, MK, and Buddy, Bad Buddy, giving. Okay, let's see how many of you can answer this. LED is a PN junction diode, which is LED. Normally it works. You pass current, forward bias. That's it. It's not in reverse bias. Yes, it is forward bias. Very good. Excellent. A for apple. Very good, Ashwin Raja. Moving on. Next question. In a full wave rectifier, rectification is AC to DC. Remember that? Okay. Full wave operating at 50 hertz. So there is AC input at 50 hertz. 50 hertz frequency. Then the fundamental frequency in the ripple. That don't get confused by this word. This is basically the DC output. It's like a ripple of water. So the final output's frequency is how much? Very obvious. If it is sine x, then it just becomes like this. It has now doubled the frequency. In one cycle, you are getting 2 ripples. In one cycle, you are getting 1, 2. So the frequency has been doubled. So earlier it was 50. Now it will be 100 hertz. 100 hertz. Very good. Perfecto. Very good. Option B. B for Bombay. B for ball. In a breakdown region, a Zener diode behaves like constant current source, constant voltage source, constant resistance source, constant power source. Come on, my warriors. Come on, my warriors. Oh my God, come on. What does a Zener diode behave like? E for Bombay? Hey, very good. Yes, the correct answer is indeed a constant voltage source. Perfecto, my warriors. You guys are smart. Voltage source. I just told you, Zener diode application. Where did it go? Constant voltage source. No matter what you do, the voltage across Zener diode in reverse bias. It's always used in reverse bias. Remember that. So it is a constant voltage source. Wow. So next topic is the new microorganisms which were discovered after virus and bacteria. So we have bipeds, so organisms which can walk on 2 legs. So these organisms which can walk on 3 legs, what are they called? B for Bangalore. Yes, Shruti. So these are the new organisms, new species which were discovered. This is how it looks like. Look at this. They look like aliens, don't they? Walking with 3 legs. Crazy. Crazy, guys. These creatures are called as transistors. Very good. Very good. So these are transistors. They don't have 2 legs, they have 3 legs. 3 terminals. And what are the terminals called? Emitter, base, collector. Jellyfish, it seems. Okay. Emitter, base, collector. And what you do is basically, earlier we had P-N junction. Pandus and Natasha. But now you become more creative. And then you invite bunch of Pandus here, bunch of Pandus here, and you place Natashas in between them. Imagine what is going to happen now. And then you become even more creative. And then you have bunch of Natashas here. And then you have bunch of Natashas here. And some few Pandus here. Think what will happen. Are you able to now simulate, visualize in your head? Crazy things will happen, no? Okay. But whatever you put in between, the sandwich, whatever you put in sandwich, okay, that has to be very small in number. Base, between, B, base, between. B stands for base, also between. And here also, it should be small. Out of the other two, the extremes, out of the other, white devil, clearly the devil. Your name should be changed to black devil now. Okay, so out of these two, one of them you place more Natashas. You place more Natashas. Okay, and on the other side, this side, you place little bit less Natashas. The one which has more Natashas or which has more Pandus is called emitter. More Natashas, emitter. More Pandus, emitter. Slightly less Pandus or slightly less Natashas, collector. So glad, Shruti. Okay, is that clear? No problem, MD, you can definitely change. So now this is emitter, base, collector. Base is lightly doped. emitter is heavily doped, collector is moderately doped. Base is very thin. Base is very thin. This is called NPN transistor. This is called PNP transistor. The three terminals are emitter, base, collector. B between, in between. As simple as that. Moore's law, Vijay Kumar, it's got to do with the size of the chips, which keeps on basically becoming half, after certain years. You don't have to worry about it. You'll study it in electronics. Okay. Now, there are three terminals. So there might be a problem connecting it because battery has only two terminals. Battery has two terminals. This weird creature has three terminals. Now you will start thinking, what to do with the third terminal? What to do with the third terminal? So basically, what you do is the third terminal has to be opened up. You make two wires out of it, and now the total wires will be 4, even in number. You cannot connect 3 wires to a 2-terminal object. Hence, one of the terminals you open it, split it, you take a wire and open it. So there are 2 new terminals which comes. So totally there will be 4 terminals. And there are 3 ways in which you can connect it. If you take the collector terminal and then you connect, it is called as the common collector mode. If you take the emitter terminal and open it and connect it, it is called common emitter mode. If you take the base terminal and then you open it and then you connect it, it is called as the common base mode. So common base mode, the base splits. Common emitter mode, the emitter splits. Common collector mode, collector splits. Rest are simple. Rest you can draw. Is it not simple, guys? I heard that, Dhaya, and I'm so glad you guys are enjoying it, Dhaya and Sanjay. Is that clear, everyone? Okay. Also, one more important thing which you should know. The base and the emitter junction. The base emitter junction is in forward bias, always forward bias, and the base collector junction is always used in reverse bias for its proper functioning. Keep this in mind. All right. Now, how does a transistor work? Let's take a simple example. Natasha, too many Natashas, too many excess friends, base, P, thin, few Pandus, very small in number over here. Again, Natashas, too many friends, too many electrons, collector. Okay? Now, what happens is, Natasha will try to give away the friends to Pandu. Pandu needs friends, so Pandu will accept also. But there are not too many Pandus. Very few Pandus are there. If there are 2,000, 3,000 Natashas, there are 5 or 6 Pandus only. Some 2,000 Natashas, 5 Pandus. Here, maybe 1,800 Natashas. Something like that. Now, Mini, yes, Bacha, you can ask. Now, what happens is, if you connect batteries like shown over here, connect the N type to the negative, okay, and the P type to positive. Remember, emitter base, I just told you, emitter base is forward bias. So notice, emitter is connected to negative, N is to N, P is to P. So because of which what happens? The negative potential pushes the electrons here. The positive terminal pulls the electrons here. Negative pushes the electrons, okay, pushes those friends from Natasha, and the positive pulls those friends, pulls those electrons. But there is a problem. The moment all these friends from Natasha's, from these N type, see the holes, they become so happy. They all start running towards the base. Imagine 2,000 friends running to tie friendship band with 5 Pandus. What will Pandu do? You only tell me. Will Pandu be able to accept so many friends? No, right? So the moment the Natashas jump, they are so excited. They are so, Shruti saying lucky Pandu. Pandu becomes famous, very true. So what happens? Very few electrons can tie the friendship band. They can become friends. But majority, because of that huge momentum, before they realize, what? Pandu, you're already friends. Oh my God, what about him? Oh, you're also friends. Oh my God, all the Pandus are friends. They all get pushed. It's like a huge crowd. Imagine, huge crowd running and they all jump onto the other side. They all go over here. They all go over here. They all jump onto the other side. Some electrons, they are in that crowd. It's like a stampede. It's like one stampede. You have to visualize this. It's like a stampede out here. Some of those friends are like, oh my God, so many people are coming over here. What do? They slowly try to escape out. And they will escape from here. They'll escape from here. And they'll be like, oh my God, I'm an electron and this is positive terminal. Let's jump out from here. Did you understand? Some Pandus, few lucky Pandus will jump from here. They will come out, slowly leak out from here and they'll come over here. Cool? Everybody understood? Understood? Clearo? Perfecto? What about these friends who got thrown away on the other side because of that stampede? You'll be like, sir, there are already so many friends. What will these new friends do here? That is why you connect it in reverse bias. What do? N you connect it to positive. The moment you reverse it, these extra friends are pulled from the Natashas. Natashas have more friends now. Natasha will be like, okay, take, you're positive, take my friends. Here, go. The moment these friends start going away, Natasha starts crying because she loses her popularity. She does not like that. When she has friends, she does not realize the value. When they go away, then she starts crying. To her surprise, it's like God's gift because they are coming from here. These electrons jump from here and come over here. And then like, Natasha will be like, okay, please come. But again, you know, Natasha is very cunning girl. She will be like, okay, I don't want to be friends with you for a long time. Again, she shoos them away. Again, she becomes sad. Again, these electrons come over here. Again, Natasha becomes very happy. And then again, she's like, okay, I don't want to be friends with you. She has attitude, man. Come on. Again, these electrons go over here. So, this is what keeps happening. Yeah, that is what Mansa, very, very chalu. She's very, very smart. Okay. So, in this whole process, what has happened? The electrons which go from here to here, part of them go here, but the rest of them go like this. So, notice the electrons coming here, they form the emitter current. They form the emitter current. This electrons coming over here, they form the base current. The electrons coming out from here form the collector current. Now you only tell me which current is equal to which current plus which current. Mood swings. Very true. Which current is equal to which current plus which current. See this. These two currents add up and give over here. So basically your, okay, what just happened? Emitter current will be equal to your collector current plus your base current. But the base current is very, very small. Very, very small. So usually you end up saying emitter current is approximately equal to the collector current because the base current is very small. Very few Pandus escape. Keep this in mind. Understood? Perfecto. And then you have these parameters. Very good JL, very good Siswa, very good Adi, very good Hari Krishna. Vijay Kumar, do I study every day? Yes, but I study every day because I have to take classes. Okay, so what are the different things that we studied till now? The emitter current is equal to the base current plus the collector current. This is the first result for any transistor. Emitter current is equal to the base current plus the collector current. Emitter current is the base current plus the collector current. But IB is very, very small usually. Therefore, IE is roughly equal to IC usually. That's what the case. Next, we have certain parameters of a transistor. You need to know that, and they are called as alpha and beta. Alpha and beta. Now, a lot of students get confused between these two. How many of you get confused? Raise your hands. How many of you always get confused? What is on the top? What is at the bottom? And do you want to know a trick to remember it? What is on the top and what is the bottom? These are basically your alpha beta parameters of a transistor. They tell you what's the ratio of the currents, what's the ratio of the currents, and from this you can understand and calculate different other things like voltage or currents and other things. Okay, guys, have you heard of this government post called as a collector? He's the collector of the district. He's the collector of this place. Collector is a very, very important post. It's a very good post, respected post. And where will the collector sit? He will be at the top. He's at the top level, right? Yes. Yes, he will be at the top. So always put current of the collector on the top. Current of the collector on the top. Understood? Fair enough? Okay. Beta, B. That's it, IB. Who is left? Only emitter. So just put IE over here. Beta B, emitter is left, just put it over there, obviously. Now you will never forget it. Understood these parameters and you can convert from one to the other very easily. Very easily, because you know the relationship between them. Hai na? Cool. Very good. Keep this in mind. Now, because we saw that a small base current is always there, and usually where is it? Yeah, there is a small base current. The emitter current is usually the collector current, and these parameters alpha beta are fixed. So I have something in mind. What is that something? If I know this is a constant, if I change IB, if I change the base current, somehow I change it. Imagine, just somehow I change it. I is equal to VR will not come. V is equal to IR always. So, if I change the base current, what will change? Collector current will change. Now think, will beta be a small number or a large number? You only tell me in the chat box. Will beta be a small quantity ratio or a large ratio? Put it in the chat box. Look at this, base current is small. Collector current is usually large. So, large quantity by small quantity. Large by small will be very large quantity. Very large quantity, correct? So, if you change this by some amount, to keep the ratio same, you have to change collector by a large amount. If you change base current, then collector current also has to change. But to keep the ratio constant, collector current has to change even more. Understood? Why are we carrying that remote? Because I have to change the slides. Without this remote, I can't change the slides. Yeah, that's why I'm carrying the remote. I can just do this. If I do this, it creates that mark. Okay. So, that changes. That can be used for amplification. What is an amplifier? You might have heard the song also. Amplifier and all that. Okay. So, amplifying means extending the amplitude, making it loud, increasing the voltages and currents, retaining the characteristics or frequencies, but only increasing the amplitudes. That's amplification. That's amplification. So, if I change base current, I change collector current, and I also change emitter current, that's how an amplifier works. That's how an amplifier works. Look at this. This is a common emitter type of amplifier. You can see that. Okay. So there is some base current. There is some current which is entering, some signal which is entering. If it changes by some amount, the collector current will change by a large amount. This is input, that is output. This is input, this is output. Understood, guys? Yes. So, by changing the base current, small variations in the base current creates large changes in the collector current. This is the output circuit, this is the input circuit. So, here the voltage gain is basically your output voltage upon your input voltage. As simple as that. Output voltage by input voltage, that's the gain in the voltage. Current amplification factor or current gain is basically output current upon input current. In this case, the output current, in this example, it is the collector current, and in this case, the input current is your base current. So that's what it is. So basically it is your beta. What is the use of amplifier? Have you seen loudspeakers? What do? They increase the loudness. They increase the volume. So it is to increase the volume. You are getting some weak signal from somewhere. You can't see it or hear it clearly. Amplifier expands it. It's like zooming in. It helps you read and understand or listen or see it clearly. That's what an amplifier does. I think we should start with some questions. There we go. In a common emitter amplifier, the input signal is applied across anywhere, emitter, collector base, base emitter. Come on. Yes, it is used to strengthen the weak signals. Perfecto, guys. So come on, answer this question. What is the common emitter? In a common emitter amplifier, the input signal is applied across. How are we changing the volume? Basically, the voltages increase. When the voltage increase, the speaker's vibrations increase. The vibrations increases, the loudness increases. That's what happens. Common emitter, that's all you should remember. Common emitter, the input is applied, signal is applied across the base emitter junction. You can see that. Base emitter junction, that's it. This is common emitter. So base emitter, you apply the input signal, output is over here. Perfecto. Next question. The current gain of a common base transistor is 0.96. On changing the emitter current by 10 milliampere, the change in the base current is. That's the question. What kind of amplifier it is? It's a common base transistor. So think about it. It's a common base transistor. So this is your transistor. This is your base. So it is something like this. This is collector. This is emitter. Common base transistor. So one will be input, one will be output. So think about it. So what is the change in the base current going to be? So first of all, you should understand which ratio you should use. Which ratio should you use? Think about it. One is the output, one is the input. So IC and IE, output, input. So IC and IE, what is this ratio called? This is alpha. And this alpha is given to you. It is 0.96. So this is 0.96. Now, if this is true, even this is true. Delta IC by delta IE. This is also true. If IC by IE is alpha, then delta of IC by delta of IE is also alpha. The change. You take the delta on both numerator and denominator. Output by input. Okay. So one is output, one is input, like you can see. Now, what is the change in the emitter current? It is given to be 10 milliampere. Delta IC, I don't know. Therefore, from this, delta IC will be equal to 10 into 0.96, which is 9.6 milliamperes. So I found the change in the collector current, but base current change is asked. Now we all know IE is equal to IC plus IB. Therefore, delta IE, change in emitter current, is change in collector current plus change in the base current. So change in the emitter current. What is the change in the emitter current? 10. Okay. And this change in the collector current is 9.6 plus delta IB. I do not know. Delta IB I do not know. So from this, delta IB will be 0.4. 0.4. 0.4, which is option B, guys. It is option B. Understood? Clearo? Shall we move ahead? Yep. Is that clear, everyone? Everyone clear about this? Perfect. Let's move on. A common emitter amplifier has a voltage gain of 50, input impedance of 100, output impedance. Impedance, think of it like resistance. Don't get confused. Resistance. Input resistance, output resistance. What is the power gain? What is the power gain? That's the question. Let's try and solve this. Common emitter amplifier has a voltage gain and okay, power gain. So power gain is output power upon input power. Power is V square by R. So that's why it will be V out square by resistance out upon V in square by resistance in. Straightforward. So this will become V out by V in whole square. This goes on the top, this comes below. R in by R out. Now the voltage out by voltage in means voltage gain. Voltage gain is given, the ratio is already given. So this is 50. So 50 square. Got it? Voltage gain means output voltage by input voltage. That is already given. Input by output. Input resistance is how much? It is 100. Output resistance is how much? 200. 50 square is how much? 2500. 100 by 200 is 1 by 2. 2 cancels and you should get 1250. 1250. Option C. Correcto. Perfecto. Isn't it? That's it. It feels complicated. It looks scary. But when you start solving, you will realize, oh my God, was I leaving transistors? What for? It's actually simple, easy peasy. Lemon squeezy it is. Just like squeezing lemons. Life's like making lemon juice. The simplest of the juice. Okay, moving on to the next question. In transistor, current in the collector is always less than the emitter current because collector current is less than the emitter current because we all know this. Emitter current is collector plus base current. So collector is always less than emitter. Why is it? Which of the following statement? Collector side is reverse bias. Few electrons are lost in the base. Collector being reverse bias attracts less electrons. Collector side is forward bias and emitter side is reverse bias. Very simple. Very simple. Some statements can be true but may not be the reason. May not be the reason. Collector is reverse, emitter is forward, correct. But that's not the reason for that. That's not the reason for that. The correct reason is B. A few electrons are lost in the base. Remember that battle? Natasha, Pandu, Natasha. Where did it go? Where did our Natasha and Pandu go? Yeah, somewhere here. Yes. These friends became very happy. Came to Pandu. Pandu made friendship only with 5-6 Natasha's friends. That's it. Many of these Natasha's friends went there. There was a stampede. And in that stampede, few of the friends escaped. Few of the base, electrons escape from the base. Remember that. So hence the correct answer to that will be, where is it? Yeah, option B. Perfecto. Wow, we have come to the last segment of today's class. And are you guys full of josh and full of energy? This class is almost for 2 hours. Next 15 minutes, I think we should be done. But after today's class, I am 100% sure you will not even think or have a double mind of leaving semiconductors and electronic devices. And if you know a friend of yours who is afraid of this chapter, you should tell them, Captain Shreyas is here on Enlite. Watch his classes. As simple as that. Let's do this. Analog and digital. Analog signals is basically like I am singing a song or I'm talking to you. My voice is changing. You have different levels, different amplitudes. You have so many variations. You can use so many words, so many tunes, so many frequencies. But digital is like, just using 2 sounds or 3 sounds, like only discrete. You are very choosy. So a digital signal is a signal where you have very limited values or certain levels only are permissible. Other levels of voltage or other currents are not allowed. It's like yes, no, true, false. Imagine talking to a person in only yes and no. That's it, only yes and no. It's so difficult. But that's how our computers work. And only using true, false, yes, no, 1, 0, high, low, whatever you call them, it's the same thing. 1, 0. high, low, true, false, yes, no. Only using that it can compute all the things which you deal with in real world. All the colors, all the calculations, all the manipulations, all the logics, all the artificial intelligence, all the machine learning, all of your computer science is just based on high and low, true and false, 0 and 1. That is why it is called as the machine language. Okay. Now, if computers can work only in highs and lows, ones and zeros, trues and false, and you have to deal with real world inputs, real world outputs, you want to deal with real world signals which have so many other logical constraints, logical operations, obviously you need to manipulate these trues and false, zeros and ones, highs and lows. There might be some operations which you need to perform. When this happens and this happens, you need to do this. Okay, and when you do this, and if this is not there, then you do that. And when you do that and this is there, then you do this also. So many logical instructions. If you have done programming, you know that. If else, while loop, for loop, right? All those are conditions. Some conditions are met. So always there are some instructions fed to the machine through the software, through your programming, and at the end your computer breaks it down into zeros and ones only. Is that clear, everybody? And guess what? Yes, guess what, guys? Only using and, or, and not, these are your most fundamental three operators. You can do all kinds of logical operations. Just like in maths, they say plus, minus, multiplication, division, and equal to. They are your operators in digital circuits, in digital signals, okay? In yes or no's or trues and false. If you just can perform or operation, and operation, and not operation, you can do all kinds of logical sets, logical instructions. Starting with or. Starting with or. Okay, I say Champa is intelligent. Champa is intelligent and beautiful. Champa is intelligent and beautiful. Now this, oh sorry, not and, my bad, I was supposed to do or. Sorry guys, or, okay, or beautiful. Now you make something called as a truth table. So there are two inputs, intelligent, beautiful. These two are called as your inputs. So inputs. So these are my inputs, and the statement as a whole will have an output. I have two inputs in this case. Imagine Champa is intelligent and let's say Champa is beautiful also. Champa is intelligent, Champa is beautiful also. Yes, it is similar to mathematical reasoning. Is Champa intelligent or beautiful? One of them at least? Yes. She is intelligent, she is beautiful. So obviously she is intelligent or beautiful. Champa is intelligent but she is not beautiful. It's okay. Or Champa is intelligent or she is beautiful. She is intelligent. No, okay, be happy. So true, false is still true. Champa is not intelligent but she is beautiful. Is Champa intelligent or beautiful? Yes, she is beautiful. Or beautiful. Or yes, she is beautiful but she is not intelligent. That's fine. She is intelligent or beautiful. Similarly, if she is neither intelligent nor beautiful, false, false. Is she intelligent or beautiful? No, none of them. Gone, false. This kind of operation, you show it like this. The inputs can be like A and B. You put a plus. So an OR operation usually has an addition symbol, plus symbol. Plus symbol is equal to your output. Let's say C. If this is A, this is B, this is your C. Input, input, output. And how to remember the logical diagram? It's called as a logical gate. It represents whatever this mathematical operation is, say, diagram wise. So, or do you see that or, do you see that in that or, I can write that or like this also, just bend it a little bit, just bend it like this. So just show it like this. This is that R's top part. You can put those two lines below, it becomes R. That's it. It becomes a OR gate. This is input, this is output. This is OR gate. This is true, this is true, this is also true. This is false, this is false, this is false. If one of them is true, then the output is true. As simple as that. Understood? This is how you can remember it. This is OR gate, OR operation, OR operation. I hope this is clear. Next, AND operation. AND. So let's see the truth table. Input, output. These two are inputs. These two are inputs. This is my output. What is the symbolic way of representing it? AND. A, N, D. Do you see the D? Just use the D. That's it. That's an AND gate. Input, output. D. That's it. Now, if Champa is beautiful and intelligent, if that's my statement, you have to see, is Champa intelligent? Yes. Is Champa beautiful? Yes. Is Champa beautiful and intelligent? Yes. Is Champa beautiful? Yes. Is Champa intelligent? No. Is Champa beautiful and intelligent? No. She is not both. Is Champa intelligent? No. Is Champa beautiful? Yes. Is Champa beautiful and intelligent? No. She is not both. Champa is not intelligent, she is not beautiful also. Is Champa intelligent and beautiful? No. Gone. And the operation of AND is represented with a dot. A dot B is equal to C. That's how you can show it. Is that clear, my warriors? Understood how that AND operation works? Perfect. Last is NOT. NOT is exactly opposite. Exactly opposite. There is only one input. The way to represent NOT, or remember NOT, that O, in that N-O-T, that O. So just remember that O and just put up a triangle. That's a NOT gate. That's a NOT gate. So if this is input, this is output, then B is A bar. You put a bar, that bar says that you're negating it. It's like reverse. It's like reverse. If the input is 0, the output is 1. If the input is 1, the output is 0. Exactly reverses it. Reverses the, whatever is given into it. That's a NOT. Now, you can have multiple other gates like NAND, D, AND plus NOT. AND plus NOT is called NAND. Just whatever output you got for AND gate, negate it. False, true, true, true. That's it. It becomes a NAND gate. You put a NOT in front of it. So that's what a NAND gate is. So you will get exactly opposite. Yep. Is that understood? N is like that half triangle. Yeah, you can say that. And NAND gate can be represented as A dot B is AND, not of that. So you put a bar over it. That is how you show it. Similarly, NOR is OR plus NOT. That's a NOR gate. You have OR, you put a NOT over it. So whatever was the output of OR, you negate it. You get a NOR gate. See, this was your OR gate. This was your OR gate. True, 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 false. So 3 falses you will get, 3 falses and 1 true you will get. Exactly opposite. As simple as that. That's an NOR gate. And this theorem, you remember it, guys, very, very important. I'm not sure how many of you know this particular theorem of, just doing this. A plus B whole bar is A bar dot B bar. This is one theorem, De Morgan's theorem it is called. And the next important thing is A bar dot B, A dot B whole bar is A bar plus B bar. You split it, but then convert dot into plus. If it was plus, make it into dot. This is what it is. You should know this law. It is called as your De Morgan's law. Very useful for solving problems. That's the only theory which is there in logical gates. If you know this, that's it. Done, done, done. Yes. Does the JEE crash course date will extend? Yes, 12th standard, it will definitely. Like we promised, even if you buy the course, even in January or February, whatever the last day of the exam is, that's the last day of validity. It will extend automatically. Here's your question. AI live में जाना सही रहेगा तभी ज्ञान फंडा? Yes, definitely. Because it is, first of all, the course is very cheap. You get the best teachers and you get doubt solving, everything. So unless you want a live class, or you can go for the live version. But if you're okay at learning at your own pace and you can watch, doesn't matter even if the classes are recorded, but the interactions, quizzes, everything are live. So please go ahead with it. Okay, so what about this? There are two sets of inputs. First time it is 0, for second time it is 1 and 0. What do you think is the answer for this? Let's see. All three are 0. The first case, all three are 0. 0, 0, 0. 0 or, this is OR gate. 0 or 0 is 0. If this is 0, this is also 0. If this is 0, this is also 0. 0 NAND. So first you think about AND. 0 and 0, if this is false, this is false. False and false is false. But the opposite of false will be true. So this will be 1. That's the first situation. Second situation, this one. These both are 1, this is 0. 1, 1, 0. If this is 0, obviously this is 0. Look at the green ones only. 1 or 1, true or true, will be true. So this will be 1. If this is 1, this is also 1. 1 and 0, true and false. True and false. Both should be true. No, false. And negation of that will be true. Hence 1. Hence both options should be 1. It's not C bacha log, it will be D. Check it out. Yes, it is D. It is D. Understood? Oh, clear? Oh, bacha log? Understood? Perfect? Very good. Shall we move ahead to the next one? And I think it should be the last question of today's class. Let's have a look. The combination of these gates as shown in the figure is NOR, OR and XOR. Interesting. Okay. Before doing this problem, just solve this part. If you short two terminals of a NAND gate, what do you think it will behave like? Think about that first. First think about that. Because if this is 0, this is also 0. If this is 0, 0 and 0, 0 and 0, 0. Not of 0 is 1. So if you give input as 0, it becomes 1. If you give input as 1, then this is also 1, this is also 1. 1 and 1, 1. Not of 1 is 0, opposite. So if you give 1, it becomes 0. If you give 0, it becomes 1. Hence, this is equivalent of a NOT gate. So wherever these two gates are there, think as if it is a NOT gate. Alright? So if this is A, naturally this will be A bar. If this is B, this will be B bar. Because this is actually speaking, behaving like a NOT gate. Now, what is this operation? This is a NAND operation and with a bar on it. So what are the inputs? Think about it. A bar is one of the input. A bar is one of the input. B bar is one of the input. Forget the N first. First think about the AND. Just think about AND. A bar and B bar. A bar and B bar. This is what it represents. This is your AND part. Now when you think about NAND, that means you have to put a bar over it. You have to put a bar over it. Now I just told you one formula which you can remember. A bar dot B bar. A bar dot B bar is A plus B whole bar. Reverse of this. So just use that over here. A bar dot B bar. Just forget that top bar over here. A bar dot B bar, just this one, is A plus B whole bar. Bar bar. What is bar bar? What is bar bar? What is bar bar? Bar bar. Negation of negation. Negation of negation gone. So it will just be A plus B. What is plus? It is OR. So actually this is whole thing is actually a simple OR gate. OR gate. That's it. As simple as that. Option B. Correct. No, A is not equal to B, A plus B, that's all. OR gate. This whole jargon is just a simple OR gate. It was in a complicated way. So if you want these kind of sessions, you want to learn all the theory of 11th and 12th grade for JEE and NEET, we have the AI crash light courses where we are teaching physics, chemistry, maths, biology, physics, chemistry, maths for engineering students, physics, chemistry, biology for NEET students with class teachers, with doubt solving. And the JEE crash course is still the last date of JEE Advanced, whenever it is, with assignments and test series. Same thing for the NEET students, PCB sessions with all India rank test series, also mock tests, report cards, doubt solving, assignments for each and every chapter, and all of this is priced at just 1,800 rupees. So as you are watching this video right now over here, all you need to do is, where did it go? Okay, I don't think my screen is visible right now. Yeah, so while you're watching this video, just go down, you will see class 12th JEE and NEET crash courses. Just click on this, it will open up the link and you will see all the important details, whatever you are going to get in the crash course, and you will see that it is only for 1,800 rupees. Even if you miss the classes, you can watch the recording again. Don't think about board exams, think about starting at least with few classes, at least those topics which are there in term 2. The same thing is also there for the NEET. You can see that right over here, and you have saved already 88% using my discount coupon code. So make sure you make the best use of the JEE and the NEET crash courses, because this will be your game changer in the days to come. Okay, this will be your game changer because you'll be competing with the real audience, with the best teachers, with the best material, with the best mock test, and you will know where you stand in the actual competition, and you will get, you know, these kind of amazing sessions that you have been getting from your teachers only. All right, fine, Naz, I'll do. And syllabus is little bit more for mains. I hope you guys enjoyed it. I hope you guys had fun. I hope you guys have learned a lot, and you will definitely share, not just share, but also word of mouth is very important. Tell your friends if they are facing difficulty in communications and semiconductors. And yes, hit the subscribe button if you have not done it yet, else you'll miss my class tomorrow on ray optics. Make sure you hit the like button, because that's how you shower your love and we get the motivation. Thank you very much. This was Captain Shreyas and I'm signing off. Have your dinner, enjoy your dinner, and stay safe, stay healthy, and keep studying. Let's rock it together. Take care. Hasta la vista.